Good afternoon, everybody. I'm Harold Asher. I'm very pleased to welcome you to this Modularity Visions track. Before I start with it, there's one announcement that the conference organizers asked me to make. As is common with conferences, students do not get banquet tickets with their registrations. So if you have a banquet ticket that you're not going to use, please hand it in to someone at the registration desk, and they will give it to a worthy and deserving student so he or she can attend the banquet. So the Modularity Visions track. As you all know, being in this community for the most part, innovations in modularity have had a really profound effect on programming languages and software engineering over getting on for 4 decades now. They shape not just the software that we write, but they even shape the way that we think about software. And I was going to give you an illustration of the fact that the software landscape is really changing dramatically and has changed significantly since the time that seminal work was done on modularity, both going back to the general software engineering community like Parnas and Dijkstra and Jackson, and even the much younger field of AOSD. But Mary saved me the trouble. Her talk this morning was a marvelous introduction to this track, in which she outlined some of the ways that software is different now and some of the issues that we need to think about. The software development landscape is also very different now. Now we have more and more distributed projects distributed all across the world. There's much more emphasis on governance, on 2 aspects of it, making sure that the software is written according to required laws and quality standards on the one hand, and also the more general issue of making sure that the software actually does what it's supposed to do. Most software is written in support of some enterprise or scientific activity, and one wants to be sure that the software actually is going to achieve that activity. And these things have become more and more important. So these landscapes are changing, and they're very different than they were. So clearly we need innovations, and among them, innovations in modularity. So when Mira and Paolo approached me about this Modularity Visions track, I got really excited about it. And really the goal of this track is to get all of you excited also. We're hoping that you'll go away thinking about new ways of thinking about modularity in new ways, thinking of new ways to achieve it, new ways of looking at it, and generally be stimulated by the discussions that come up. Of course, to use an old English expression, we don't want to throw out the baby with the bathwater. In other words, there are some very important properties of modularity that we've come to value and rely upon. We need to understand what they are, and going forwards, we need to either preserve those properties in the new forms of modularity we look at, or at least we need to understand the trade-offs very well, so that if we sacrifice some valuable benefit, we need to understand why and what benefit we get in exchange. And the kind of analysis that Mary was doing this morning with a framework is a beginning of, or on the path to really understanding that. So in this track, we've got an interesting mix for you. We have another keynote talk, which due to travel problems is going to be on Friday afternoon instead of tomorrow morning. We have 2 invited talks. We have 2 paper presentations, and we have a retrospective on modularity, which is a special session that's also a celebration for the 10th conference. The keynote and invited speakers are from the broader HCI, software engineering and programming languages communities. So as you'll see when I introduce the speakers, they've done work related to modularity, but they haven't really worked in this community before, and they bring fresh perspectives to us that I think we'll find very valuable. As far as the papers are concerned, we had an open call for high-quality modularity visions papers. We received 9 submissions, of which 2 were accepted. And we also had a 2-phase submission process, a little different than the research papers, but the same principle. And it was really helpful. The 2 accepted papers were both papers that were submitted in the early phase and were revised. And so, like Chiba said this morning, I strongly recommend that if there's whenever there's such a process in future, submit papers early. It really does help. 3 papers were judged to have some really interesting ideas that we wanted the community to hear about, but the papers themselves were not suitable for publication. So what we did was invite the authors of those papers to present what we call core idea presentations. Just short presentations, not full papers presentations with details, but just short presentations to put across their key ideas. Unfortunately, only 1 set of those authors could actually come to the conference, so there's going to be just 1 core idea presentation, and that will be on Friday afternoon also. I now want to call on Dick Gabriel just for a moment to talk about the retrospective on modularity session and some preparation for it.
So the retrospective will be tomorrow afternoon. The idea behind it is quite simple, which is to look at the history of the ideas and how those ideas affected people in our community. What we're going to do is go through the timeline in historical order. The individuals whose names are on the items will get up for just a few seconds or a minute or two and either talk about a reference, talk about a story, talk about an idea, whatever is relevant to the sort of history of the concept of modularity. So we've been working on it online for the last few months. Out there you'll see some sticky notes, so if you want to add to it, write your name on the sticky, a little note that sort of says generally what you're going to talk about, 1 or 2 words, and stick it on the timeline where it belongs. And we'll have Gregor at least on Skype, so we're going to have a great time. Thank you.
Thanks, Dick, and of course thank you also for running the session. A couple of other thanks. Thanks very much to Mira and Paolo for proposing this. Thanks to the Modularity Division's Program Committee for their work in evaluating the papers. Thanks to my 2 primary advisors on this, other than Mira and Paolo, namely Dick and Perry Tarr. I had a number of discussions with them, and a number of the good ideas for this track came from them, so I'm very grateful. And Dick, yet again, served another important function of handling the one paper with which I had conflicts of interest. So multiple thanks. Okay, so now we can get down to this session, and I'm very happy to introduce the first of the invited speakers, Jim Herbsleb. Jim is a professor at Carnegie Mellon in the School of Computer Science. Before that, he led the Bell Labs collaboratory project, which examined issues in geographically distributed software development. In general, the focus of his research is on collaboration and coordination in software and systems engineering projects. And he tends to iterate over empirical studies, theory development, and design and deployment of technology, which I think is a really good cyclic way to do it. He's associate editor of ACM TOSEM and an editorial board of Empirical Software Engineering Journal. As you can imagine, his publication list is pretty impressive. Last year in Cape Town at ICSI 2010, he and his co-authors won the Most Influential Paper Award for the ICSI 2000 paper entitled A Case Study of Open Source Software Development, the Apache Server. Several other of his papers have won Best Paper Awards or Distinguished Paper Awards, whatever the conference was giving. And this includes 2 seminal papers in an area that he has pioneered called socio-technical congruence. So we're all used to the fact that modules in a system are structured in a certain way and have certain kinds of dependencies. We also know that the groups of people who work on software have certain interconnections and interactions, and that they have a certain social structure. And the idea is that the alignment, or in too many cases the lack of alignment, between the software structure and the social structure has great impact on software quality. So we in this community are very focused and have tended to be very focused on the one side of this. We look at all kinds of ways of structuring artifacts and composing them and analyzing them, and we tend not to look much at the social side of things. And Jim's work has clearly demonstrated and proven empirically that the social structure and its relationship to the software structure is critical. So this kind of broader view that he has shown is exactly an example of the sort of broad and a new perspective that we need to take. And so I'm really particularly pleased to welcome Jim to inaugurate this very first Modularity Visions track.
Thank you. Thanks for that great introduction, Harold. So I'd like to start out my talk by briefly addressing the question, what is modularity? But in fact, I don't have to do that. The advantage of not being first in a conference is you can kind of take advantage of what went before you. And Mary, as you know, did a great scholarly, insightful analysis of the question, what is modularity? Basically saying about what I was planning to say. That's a joke. I had no idea what to say. And I'd also like to thank Dick. So he's going to lead the session where we not only find out what modularity is, but how it got to be that way, which I'm looking forward to. So I'm not really going to pay much attention to the question of what is modularity, but I'm going to pay a little bit of attention to the question of why modularity. So I would argue, this is an extreme position for the sake of painting a target on my chest and getting discussions going, software modularity doesn't really matter at all, except to the extent that it modularizes the work that people do. Okay? And the reason that work modularity matters is because it aids human understanding. You don't have to understand everything to understand enough to accomplish something. Right? And it also simplifies coordinating people and teams working together on projects. Now, I should point out that I'm in pretty good company taking this point of view. I don't know if you know the famous social scientist, David Parnas. If you do know David Parnas, you understand the kind of how outrageous it is to call him a social scientist and how unhappy he would be with that characterization. But nevertheless, I think he has contributed to our understanding of the relationship between social science and software. And if you go back to his classic paper, which I've cited at the bottom on information hiding, he describes the expected benefits of modularity. And one is to reduce the need for coordination. Right? The quote is, separate groups would work on each module with little need for communication. Second one is to simplify comprehension. You can study the system one module at a time. And finally, these effects lower the cost of change. So you make drastic changes as long as they are confined to being within the module. So I think that the great social scientist David Parnas actually agrees with this view, and that was one of the motivations for the whole notion of information hiding, which is a key to modularity. All right, so that's what I want to say about modularity. Now, I'm supposed to be presenting a vision, so I thought I should figure out what that means, what should a vision be, so I made immediate recourse to Google, of course, and found out that a vision is a vivid mental image, as in he had a vision of his own death. That actually came to the top. That creeped me out a little bit, so I continued Googling and found this helpful definition: an explanation of life founded upon the writings of Herodotus and upon certain doctrines attributed to Custa ben Luca. Now this, surprisingly enough, turned out to be a dead end, so I had to abandon that. But this one I liked a bit more: a thought, concept, or object formed by the imagination. So the notion is that there's a lot of imagination involved here. We're not talking just about things that have been verified or for which there's extensive evidence, but this is kind of a leap of imagination that I hope you'll make with me. But I also found this, a direct mystical awareness of the supernatural. This is much more popular in the 60s when it was accompanied by the use of certain hallucinogenic substances. But I'm actually going to try to avoid this particular kind of vision. So I'm going to be sort of walking a fine line between imagination and delusion, and you can tell me how well I do that. Okay, so I want to start out with this notional sort of graph to understand, to sort of frame what it is that I'm really trying to address here. So on the x-axis, we have the number of language-based modularizing mechanisms. I don't really know how to count them or how to say exactly how many there are, but this is just notional. We can imagine that there's more or less, many are more or fewer. And on the other axis, we have something like the proportion of dependencies that cross-cut these mechanisms. Okay? So this is just notional. Don't ask me to define any of this because I will just refuse to do so because I don't know how to do that. Now, so back in the bad old days of spaghetti code, go-to statements, essentially no ways of modularizing anything when the life of a program was nasty, brutish, and short. Everything was potentially related to everything else. There was no modularization. So you have 100% cross-cutting in some sort of a, kind of a degenerate case, since there's nothing, everything's cross-cutting, there's nothing to be cross-cut. And of course, the cognition and coordination problems were huge. right? Everything that was not handled by modularity has to be handled by people searching through the code, right? And potentially very large volumes of code. And teams coordinate by continuously kind of talking to each other, trying to keep track of what the other team is doing so they don't step on each other, right? Now with traditional modularity, you get a sudden drop in this. All of a sudden, everything from while statements replacing go-tos to the farther reaches of traditional modularity have made a lot of advances, no question about it. Cognition and coordination problems are substantially reduced. And I guess aspects kind of fits into the picture as another key modularization technique that has further reduced cognition and coordination problems. And in the future, we'll be seeing many more of these. I don't know. Presumably, there will be more. They will contribute to our ability to handle these kinds of problems. Now, I'm just guessing this picture as I drew it might not be exactly the way people here see the picture. I'm just guessing. But I suppose you might see it more like this, with traditional modularity sort of coming in there and aspects kind of coming in here. Who knows? I haven't even defined the axes, so who can say, what's contributing how much to what? But here is sort of an exaggerated version of what I'm claiming to be my view, which is that there's sort of an asymptote here in the number of modularization techniques. And I don't know where it is. I don't really want to try to put a percentage on it. But the point is, I think it leaves a huge number of these cognition and coordination problems unsolved. And the reason I have this view is partly because I think it's true, but partly because it's this gray area in which I tend to do my work. What are the things that are left over that need to be handled? And I really think that the gray area is, and this is sort of one vision, it's sort of a dystopian vision, if you will, that modularity alone will never fix the problem. And I think there are a lot of reasons for that. Part of it is, the whole list of things that Mary talked about today that create continuously needs for new kinds of modularization. So what's out there and deployed in the world seems to continually run ahead of our ability to simplify it. Right? We're trying to catch up all the time, but we'll never catch up, in my view. And things also, even in older systems where you don't have all these new kinds of things to modularize, in systems that have been around for a long time, there is quite a bit of evidence that modularization gets less effective with time. Okay, so you design a modular structure, or you design an architecture, you decide a set of components, and more, you're using those for things that you didn't anticipate, right? So all design decisions are with respect to sort of what you plan to do in the future, and once you deviate from that, and you're doing things that you never anticipated with the design, that modular structure is not going to work very well. And there's a lot of evidence, actually, to sort of back that up. All right, so there's the dystopian part of the vision, if you will. So how do we approach the gray area? This is kind of the substance of what I want to talk about today, is this approach. And I claim that things like organizational design, work assignments, and tools that are set up to bring the right dependencies to the attention of the right people so they can act appropriately, provide an approach. I don't know if you want to call it, I've played around a little bit with calling this sort of dynamic modularity, modules that are kind of created on the fly based on what you're doing. But I've had significant pushback from people who know what they're talking about, so I try not to say that too much anymore. But that's kind of the view, that's kind of the vision, that you know enough that you can kind of construct modules as you go based on what you need now, based on what you're doing. Okay, so the bulk of the talk is that I want to provide two examples. One talking about organizational design and work assignment in an area that I think shares some commonality with aspects, and that is feature-driven development. I'll describe how I think features are in a way similar to sort of cross-cutting concerns and similar to aspects. And the second example is using information from the environment, learning from human activity to enable ways of kind of constructing these module-like groupings on the fly, if you will. And after that, of course, I will lapse into wild extrapolation and try to maintain my balance of vision versus hallucination. All right, so what I want to do is talk about a study in feature-driven development. I'll just pull out some of the results. This is a little bit of a preview of a paper that Marcelo and Contaldo and I wrote, which is going to be an ICSI this year. So I'm just going to give you a little preview of some of the results because I think they're relevant to the topic. All right, so what is feature-driven development? It's very hard to define a feature in sort of the same way it's hard to define a concern or anything else that's kind of cross-cutting. But it's a kind of a unit of functionality that's in end-user terms. This is something that a user wants the software to do. Right, some kind of semi-atomic unit of what the user wants the software to do. So you might, in a word processor, for example, spell checking could be a feature, for example. Something that from a user's point of view is a piece of functionality that they want. And features in many, many domains tend to cut across traditional software entities. Right, in telecommunications, so as Harold mentioned, I was at Bell Labs before I came to CMU, and this is just ubiquitous in telecommunications. If you're building some feature that's going to be on a device in a network, you pretty much have to modify many devices on the network to implement that feature. It's a rare exception if you can stick with modifying one component to implement a new feature. So they tend to cut across traditional software entities. And the way the work is done, the way I've always seen it done, although I'm sure there are other ways of doing it, is that the feature development is assigned, the responsibility for it is assigned to a feature owner, and then you have a team who works kind of under the supervision of the feature owner that actually does the work. It's kind of an ad hoc team. It's put together just for the purpose of implementing that feature. And in the usual case, the developers are associated with components, so your full-time job is to work on component A, B, and C. But then the way the work gets done is for feature 1, I need a developer from component A, one from component B, one from component C. They will become the feature team. They'll implement this feature. Then they'll all sort of split apart and be assigned to a new feature team. So this is the way this kind of development typically works. So the thought, of course, is that if we can learn something about what makes for effective feature-driven development, those lessons might translate into what makes for effective development that cross-cuts in other ways. So the particular study that I'll mention, we looked at software for an automotive navigation system. There are about 1,200 features, close to 3 years of activity, about 180 engineers, 13 teams, 1.5 million lines of code. This is all just to kind of give you the idea of the sort of system we looked at. It's pretty sizable. There was a complete architecture description put together and maintained by the architects. And it had 107 architectural components, and the files were mapped to these components. And this wasn't just their first stab at feature-driven development. They had developed this way for at least 5 years before we started the data collection. So these are experienced feature-driven developers. And the way it works is the architects would put together a feature development specification which would specify exactly what changes were to be made to which component in order to implement this feature. And that specification would be handed over to the feature owner, who would then recruit members from those components to work on this feature development. Okay, so that's kind of the picture. That's what we're looking at. Now, this, for statisticians in the crowd, if you're interested, this is actually the results of a hierarchical linear regression model. You don't really need to know that, but if you're curious, that's what you're looking at, in which we used a number of variables to predict integration failure. Right, so the way it works is that when the feature development team feels that they're done developing the feature, they hand it over to an independent testing team that does integration test, and at the same time runs regression tests on all the prior features to make sure that this new feature didn't break anything. And if the new feature fails the integration test, then we count that as a failure, obviously. If it does not fail, if there's not a single problem, then we count that as a success. Okay? So what we're doing is looking at what, of all the things we can measure and that seem like they might be related to causing integration failure, what actually causes integration failures in this kind of feature-driven context. All right, so one thing that was a little bit surprising is that, and by the way, these numbers that you're looking at over on the right-hand side are what we call odds ratios. A ratio of more than 1 means that that factor contributes to the likelihood of failure. A number less than 1 means that it helps to head off a failure. Right? The failures are less likely where that is present. Okay? And the asterisks, 2 asterisks, mean it's highly statistically significant. Okay, so just looking at factors, what causes integration failure, the concentration of the number of dependencies makes something more likely to fail. And what this means is that if the dependencies among the components that are changed to implement this feature, if the architectural dependencies among them are kind of evenly spread across the components, it's more likely to fail. Okay, that's what this is telling us. Interesting, a little bit counterintuitive. So unsurprisingly, for those of us who have studied this topic, if the feature development is done by a team that is distributed across sites globally, it is approximately 14 or 15 times as likely to fail as if the whole team is local. Again, not too surprising. Now here's something that we kind of suspected but weren't sure about. It makes a very big difference who the feature owner is, and in particular, if the feature owner is a member of the component team for the most highly coupled component, that has a powerful effect of preventing integration failures for development of that feature. Right? So that makes a big difference. The highly coupled component, the one that's touching the most other things, if the feature owner comes from that group, you're much more likely to succeed than if the feature owner comes from elsewhere. And something that was a little bit surprising is that the concentration of the number of dependencies interacts with the owner belonging to the most highly coupled group. Now, interactions are hard to describe, so let me show it to you in a graph. What we're showing here on the y-axis is the probability of integration failure, right? So from 0 to, I think the topmost point is 0.5. On the x-axis, we're looking at the concentration of the number of dependencies. How concentrated are the number of dependencies? Okay, so we see that as we move to the right, that means they're more evenly distributed. Having the feature owner belong to, so where the, sorry, I guess I can't walk, I'll do the lounge act thing here. So what we're seeing here in the red line is the feature owner does belong to the most concentrated component. Well, as the number of dependencies increases, or the concentration of dependencies increases, so that they're more and more concentrated in the feature that feature owner works on typically, the probability of integration failure doesn't really go up that much. When we get out here with really high concentrations, having the feature owner come from that group is really, really important. There's a huge difference in the probabilities of failure in those two cases. Now, another thing we looked at in this study is feature interactions. So when you integrate a feature, you can break other features. Right? Features often interact in kind of destructive ways. It's been known for some time. It's a big problem. So can we look at the causes of these kinds of destructive feature interactions? What causes integration of one failure to result, to result in the failure of a feature that was previously integrated? That's the probabilities that we're looking at here. We're trying to predict that. So some of the factors that seem to make a big difference, and how many groups were involved in these two features? In other words, how many component groups were involved in creating them? What was the overlap among groups? The more overlap between those groups, right? The less the chance of failure. Did the same person act as feature owner for these two features? Very powerful effect. If you just assign the thing to the same person, they're going to be in a much better position to overcome potential destructive integrations. GSD, again, had an effect. If they were developed in different places, they're more likely to act in a destructive way. How many cross-feature dependencies are there? How many dependencies among the changes made for the first feature and the changes made for the second? Seems like something that should clearly be a problem, and it is. Now here's one that is really interesting. GSD, or Global Software Development, interacting with a number of cross-feature dependencies. Now let me show you a graph of this, and I'll show you why it's very surprising. So here again, probability of an integration failure. And here, the number of cross-feature dependencies. This is actually the log of that number. For statistical reasons, we had to use the log. And for globally distributed teams with relatively low numbers of dependency, there is a higher rate of failure, you know, for any given value of cross-feature dependencies, right? So that's kind of what you'd expect. Globally distributed teams do worse. They're more likely to have destructive feature interactions. The surprising thing is when you get out on this end, when you have really high numbers of cross-feature dependencies, the globally distributed teams globally distributed teams do better. There's more probability of failure for the non-globally distributed teams than the globally distributed teams. Now that's kind of surprising. Why should they do better ever? And the only explanation that we can come up with, this is kind of tentative, is that, you know, co-located teams, well, obviously co-location doesn't scale in the number of people, but it also, whatever techniques they're using to coordinate the work, it doesn't scale in the number of dependencies either, apparently, right? So if you have very few dependencies that you need to manage with your colleagues along the same corridor, you can handle that fine through whatever kind of informal means your team might use. We don't know that all the teams are doing the same thing here, but teams have ways of managing dependencies among themselves. But once it reaches a certain number, those things really break down, and managing them in the more formal ways, you know, with more frequent communication, with other techniques that the globally distributed teams are using, turns out to be more effective, even though they're split apart, which is interesting. I think that says something about how to manage, you know, cross-cutting kinds of things. And if you notice, it's kind of a log scale on the bottom, so that kind of, the effect, the crossover would be much farther to the left, and the effect would be much more pronounced even if we were just using regular linear scales. Okay, so what broader lessons would I have you take from this? Organizational arrangements matter. We've known that about many kinds of development for a long time, and what we're seeing here is evidence that in managing the development of features, you know, things that cut across traditional modules, we are understanding the kinds of things that matter here. The effects can be quite large, right? From the 14 to 15 times for GSD to things like, you know, 15 to 20%. Just by assigning the feature to the right person, to the right feature owner, you can reduce the likelihood of failure by 20%. That's pretty large. And finally, the effects are often not what you would expect from a common sense point of view. I mean, we really do need research here. Who would have thought that GSD teams would have an advantage for some kinds of things? For highly interdependent components, they have an advantage. Very unexpected. At least it was totally unexpected to me. All right. So that's the first example. Now let me move on to the second, then I'll spend a little bit of time trying to sort of tie them together in some way. Inferring dependencies from traces of human activity. There's been a lot of work now. There's a whole conference co-located with ICSI on mining software repositories, and this kind of work is very typical of some of the things that go on at ICSI. And part of the work of using software repository data to predict interesting things is using that to sort of predict dependencies among the work that people are doing. So we did some work a couple of years ago where we used very simple kinds of things like files changed together as a measure of dependencies, right? Rather than doing an analysis of code, We look at what files typically get changed together in addressing the same modification request, use that as a measure of dependencies. It turns out that works much better than analysis of things like call graphs for our purposes. From this, you can generate a measure of coordination requirements, who has to, based on what files people are touching, who has to coordinate with whom in order to get the work done. And we validated this in a number of settings over the years, showing that when people's coordination activities actually line up with our computed coordination requirements, the quality of the code is higher, the amount of development time is shorter. In other words, just in general, good things happen. So what I want to talk about next is kind of an extrapolation of that idea. Files changed together only works for code, right? Are there ways of using this kind of insight to predict dependencies of other kinds of artifacts and using all sorts of data to try to do that? And in particular, think about technical discussions where you have teams talking about discussions at stand-up meetings or technical meetings of various sorts. We got an awful lot of mileage out of inferring dependencies just from things that were changed together. These two files are changed together, well, there's probably a dependency. How about if we just look at things that get discussed together? Gee, among experienced engineers, every time they talk about this, they also seem to talk about that. Could that be used to infer some kind of dependency between them for other people who are maybe less expert in that exact topic? And yeah, that's the kind of idea that we're sort of advancing here. So a brief digression at this point. It's a bit of a leap, right, to think about going from kind of language constructs and things that you can kind of logically infer, things that you can see in a language, to using numbers to predict dependencies that might exist somewhere, okay? And many people, including me, anybody should have a certain healthy skepticism. Just computing stuff from all these numbers is kind of iffy, maybe you get a lot of false positives, maybe not. We seem to have some interesting issues. So I want to sort of show a comparison, which may or may not be convincing, but I think it's interesting either way. There was a disagreement in AI circles a few years ago. So I used to do a little bit of work in AI back in the mid-'80s. There actually was AI back in those days. We had to use an abacus, but it was a little slow. But at that time, most AI meant symbol systems, right? So you're doing computations, usually using Lisp to sort of cleverly apply functions to lists of things. Most in AI was thought of as sort of search through space and so on, a guided search. And there's very little use of numbers. Right? And then machine learning kind of began to take off in the mid-'80s. And it seemed to all the symbolic AI people as though machine learning was just kind of wrong-headed. You just put a bunch of numbers in there and try to predict stuff, and all right, thank you. Seems to be the worst. Oh, now it's on. Good. So the problem with machine learning, suppose that you do come up with some learning algorithm that does some, produces the right answers. Okay, so now you have a bunch of parameters that were set empirically. What have you learned? This is driving me a little bit crazy here. So a lot of people thought of machine learning as just kind of wrong-headed. Well, the success of machine learning since then has been pretty startling, right? You don't really hear very much of AI and symbol systems these days. So just to prove this point, being sort of empirically inclined, I went to Google. What do they call it? Google Labs Books Ngram Viewer. This looks for occurrences of selected terms in all books published. When did I start this? 1950 or something. And I looked at symbol systems and machine learning. And if you look over time, the red is symbol systems. And through the 60s and 70s and up until the mid-'80s, symbol systems you saw a whole lot. right? Symbolic reasoning was it. That was the whole deal. And then, whoops, machine learning, all of a sudden, when machines got powerful enough and very clever algorithms were invented, starting in the 80s, machine learning sort of shot up through the roof. And all of a sudden, talk about symbol systems sort of, you just don't see it much anymore. Now, I'm not saying that proves I'm right, but it's interesting. Right? It's interesting. Okay, so I want to tell you a little bit about one we made. A psychology experiment or something. Damn students, you know. You never know what they'll try next. You know. So anyhow, we were looking at a text analysis of a field robotics project, right? And we wanted to be able to understand the dependencies on that project in order to help the team set up their collaboration technology, okay? Now this was part of the Lunar XPrize competition. CMU has been building a robot to compete in the Lunar XPrize competition. Are you familiar with the Lunar XPrize competition? Google, wow. How many do you have back there?
Just try not holding the back.
Not holding the bottom?
Yeah, that's not holding, yeah, that's it.
So this is an iPhone antenna or something? Okay. So the idea of the CMU team is to build one of these. This is actually a CAD rendering of one of the prototypes. And to win the Lunar XPrize, they have to figure out how to send this to the surface of the moon, land softly, preferably, and run around, cover at least 400 meters, and send back high-definition video. And the price tag's a mere 125 million or so, and they're in the process of trying to raise money. So the project that we were looking at was basically trying to design this, the rover, okay, that has all those kinds of capabilities. So there is nothing like automatically collected version or change data. This is a bunch of students and some faculty members trying to hack this thing together. And they don't do change control for too much of anything. For some of the software, they actually do. Bless their hearts. Glad to see that. But if you're looking at the whole system, things are not under change control. Constantly shifting component boundaries and interfaces, right? They're constantly trying to solve problems. They're under, very tight requirements for weight and for power and all sorts of things. And so they're constantly throwing out old designs and kind of scrambling things up. So what we wanted to do is to try using text analysis to sort of derive the dependencies in their work, to see if we could provide any leverage to them in understanding how to sort of keep this project on track. It involved about 30 people at CMU. It involved some former NASA scientists. It involved people from several large firms that develop rocket stuff. So I would tell you who, but there have been different restrictions on who I'm allowed to tell what over the few months, and I don't really know who I can say what to anymore, so I just won't say anything about who the industry partners were. Can we use text analysis to derive some of these dependencies? So here's what we did. We collected some data, which seems like a good thing to do. We collected data for the better part of a year. We couldn't use it all. They had these weekly meetings. We decided these meetings might provide the richest source of data. At these weekly all-hands meetings, as they called them, they went through what had happened during the previous week and did planning for the next week. And they did it kind of by area, right? So they would have a discussion of the optics for the rover. How are we going to do the optics? So the leader of the optics team would describe what they had done. Other people would chime in with, oh, well, if you're going to do that, that creates this problem over here, and so on. So then it was at this meeting that all the things that weren't handled internally by a particular functional team got put in front of everyone else, and they had a chance to comment on, discuss issues about how these different things interacted with each other. So we thought that it's at these meetings where we might have the best opportunity, right, to learn about how the different components sort of interact with each other and how they relate to each other and affect each other. So we collected data, we recorded and transcribed 25 of these. Actually, we had 30-some, but for reasons that aren't that interesting, we couldn't use it all. But we had 25 usable meetings, about 10,000 words each on average. And we developed, the first step was to develop a code book. Right? We have to have sort of a canonical terminology to describe sort of the high-level components of systems like this. So we went out to the robotics literature, and we found articles in field robotics. Field robotics is the kinds of robots that go out and do stuff on their own without any remote control or anything, just sort of make intelligent decisions, and they operate autonomously. It's really scary what some of these things do out there in the wild. But anyhow, so we looked at a number of articles on those, and we sort of pulled out the terminology used in each of these articles to describe the components of their system. Okay? And then we developed from that a code book trying to find what are the components that appear, and then we can sort of try to figure out a common terminology for those components, so whenever they're talking about one of these components, we can map it to one of these kind of canonical terms. All right, so this is a very labor-intensive manual process, developing the code book. So here, we worked on this for many months. Here's kind of the final version of the code book. I think it has 11 different components and a brief description of what each one is. Then we went through and did a manual coding of the discussion decisions. So we went through transcripts, in other words. 3 of us did this. And we tried to sort of segment these transcripts in terms of decisions. The notion is that if two components are being discussed in the context of a decision that the team is trying to make, there must be some dependency between them. Otherwise, why would they be discussing them together repeatedly? Okay? So we segmented the transcripts at each point where they seemed to be changing the topic from one decision to another decision. And this is difficult to do, by the way, if you've never done this, but we segmented the transcripts that way. Then we went through and said, okay, what of these top-level components are mentioned in each of these decision discussions? And then we sort of just created a big table of co-occurrences as our representation of the dependencies among these things. And we coded this manually, individually. We looked to see how well our coding correlated with each other, and it turns out we got CRAP is just this way of correlating networks, which is what we were getting out of this. And iterated reliability was 0.8. We finally got to that point, which is actually very good. So we felt like now we really have a set of categories that are meaningless. We're not just sort of randomly applying these, but we're all using the terms in the same way, pretty much. Then we did a bunch of text pre-processing that's not all that interesting, but things like stemming and getting rid of contractions and so on. We created a thesaurus. So this is kind of an interactive process if you've ever done this. You find words, for example, that are used in pretty much the same context as some of your keywords, and you realize that, okay, those are synonyms for this word that we have. And there's this iterative process you can go through to create a thesaurus, which basically gives you all the words that are actually used in the data out there that map to these canonical components that we identified from our analysis. So we created the thesaurus. And so now we have, doing that, basically we have a way of going through the transcripts and pulling out each occurrence of, a mention of a component. But we don't have links yet. In the manual case, when we're trying to automate this process, is something I failed to mention. The links are created in the manual case by noting the two mentions of a component occur in the same decision discussion, right? So that's how we infer that they're linked. And we get the link strength by how often that happens. But if you've ever done this, you'll know immediately why we would like to automate the process, because this is torture to do this. It's just not a lot of fun. So what we needed to devise was a way of automatically inferring these links. So we took something fairly simple. We didn't know how well it would work. But we took sliding windows, right, of different sizes and slid them over the transcript. And so The machine can't really figure out when the discussion goes from one decision to a next decision, but if terms co-occur within the same window, we can start to infer links that way. We don't really know how well that worked at the beginning, but we started experimenting with that, and we found that a window size of about 15 words had pretty good agreement with the hand coding, and it kind of makes sense based on the length of sentences and topics that people discuss. This seemed to be a pretty sensible amount. And better yet, when we ran it over the transcript, so we had coded by hand, we got about the same correlation. So this kind of machine scoring agrees with humans just about as much as humans agree with humans in their scoring, and it's a pretty acceptable level. So we have sets of links then based on topics, because as I mentioned at these meetings, they went through a series of topics, and so we wanted to then see what the links for these topics looked like. Now here's why it might be interesting to this crowd, because these are a little bit like concerns. So all the components of this rover, and by the way, there's a little bit of discrepancy between the terminology here and the code book. The networks were generated from a slightly earlier version of the code book, so if you look at those carefully, you'll see they don't exactly line up, but nevertheless, I hope they illustrate my point. So optics gives you kind of one view of the system. You're concerned with how you're going to get the images you need and store them for later transmission. And so it shows that things like communications is very tied to the perception software, right? Software that's processing the data from the cameras, the kind of communications you need, and the bandwidth you need and so on to send that stuff back to Earth depends a lot on the kind of software you use for the communications. You can see that testing joins a bunch of things: communications, mission-specific effectors, requirements, sensors, structure. Because what you're doing when you test, in this case, is basically build a prototype, take it out to this place we call Robot City, and run it around and see what breaks and see what doesn't work. And so the testing has an impact on lots of different components. External relations here means basically a lot of the work here was shopping, strangely enough, where you're looking for this type of computer to plug into your rover or this kind of motor and so on. And so in this case, in the meetings we looked at here, there was a lot of discussion of the structure and how to fabricate that and who could do that out in the external world. So anyhow, here's an optics view of the rover. The thermal view is very different. This has to do with heat being generated, heat being transferred from one component to another, devices used to cool it off. It also has some connections to the structure, because if there's too much heat, the structure will degrade. It has some connection to the power, because if the batteries get hot, they have less power, so there's linkage there, a thermal linkage. And the avionics box, this basically is the avionics box in this discussion. It's just sort of a general purpose computer that basically runs a lot of different things. And so it's hooked to everything that has computational, uses computational power, but also to things like prototype fabrication. Where do we put this thing? Where do we put this box inside the robot, right? So, and different boxes that we might use have different requirements for weight and size and so on. All right, so the notion is that the gray area, I think, is here to stay. Work that cross-cuts language constructs will always be with us. There'll probably be lots of it. It's always going to be racing ahead of our ability to make sense of things from a language point of view. Organizational tactics can make a surprisingly large difference in how we manage these kinds of cross-cutting concerns. We can also use computations over artifacts generated by development activities. I think we've shown that fairly well for things like files that are changed, version control systems, and so on. But I think we should explore lots of new data sources, including documents, even conversation. Voice to text is good enough. Why not wire up everybody working on a project and use that as data from which you can figure out dependencies? The notion is that activities and what's spoken by humans reveals a lot of knowledge. And there are techniques we can use. We're just scratching the surface, but there are techniques we can use to make this knowledge actionable, right? To sort of support the idea of creating the modules you need on the fly. Show you the stuff you need when you need it. That's it. Thank you very much for your attention.
Mira Mazzini, Technische Universität Darmstadt in Germany. I have two questions actually, and excuse me for my voice, it's away since days. The first one, you said modularity doesn't matter.
Except.
Except, I agree. No, and you explained what you mean by this, and I fully agree with you that all the things you talked about are as important. My question is, nevertheless, do you think it doesn't matter at all, or we need actually a combination of both? Better modularity in the language and better modularity in the kind of modularity you are talking about. I would call this also modularity, right?
Yeah, great point. So, no, I think at the moment, modularity is by far and away our most powerful tool for managing dependencies. I mean, all of software engineering is kind of based on different forms of modularity. And I think that, you know, coming up with new ways of modularizing the kinds of things that Mary was talking about, for example, I think that's extremely important. So I have no disagreement with that at all. I think we need, but all I'm saying is I think we need more than progress in modularity, because I think we'll never get to an end point, and there'll always be this stuff, a lot of stuff, kind of hanging out that we can't localize. And so what do we do about that?
I wonder whether the technique, the kind of modularity you talked about, would be even more effective combined with better modularity at language. I mean, what the relationship, we don't know probably, right? At least I don't know studies of how good those techniques work for different kind of programming languages, code written or software development processes and all that. But my second question is, all this involves a lot of gathering of a lot of information about the process itself, about the people in the process. And I agree that it's very, very valuable. We do some work on that area in my group, where we learn from existing code, from how people interacted with development environments. And whenever, I mean, the developers out there, we go to companies, they find it great. But the second question, at least in Germany, is that, but what about privacy? How would you, I mean, are you allowed to gather this information and to map back who did what?
Yeah. Well, great question. Great question. There are definitely privacy issues. I have no idea what to do about them. Yeah, so I mean, I think what I mapped out here is like a first step in a research program that will have to go a long ways before it actually becomes practical and useful. And along the way, a number of issues have to be solved, like how do we collect the data, what are the right analytic techniques to use, and what are the right ways to present it to developers, what's the relationship between this sort of approach and the existing modularity approaches, because I agree they're going to be much better if they can be combined. I mean, the modularity approaches, the language-based modularity approaches you're using kind of determine what sorts of stuff will be outside them. Right? So I would imagine that tuning these two kinds of approaches to each other would be much more effective. And so among the many, many problems that would have to be solved along the way, you know, ensuring the privacy of developers is certainly one of them. And I, at the moment, don't really know how to do that.
Do you have an idea whether it's more effective just to ask developers what they think that the dependencies are versus mining this data?
Yeah, good question. So the two things I want to say is that if you ask the right developers, you probably get as good or better an answer. What we've seen in some of our other work that we published a few years ago was if you look at how well the very best developers use their communication channels, it turns out that their use of the communication channels is extremely well aligned with the dependencies as we computed them from the artifacts. Okay? They're very, very high in congruence. But that's only about the top 10% of the developers. The other 90%, there's very, very little alignment, actually, between their use of coordination tools and the coordination requirements that we computed. So I think part of the answer is you'd like to get the knowledge that the best developers have out there for everyone. So if the best developer knows that if you touch this, you better look at that, then everyone, when they touch this, should have that information without a lot of false positives and so on. So yeah, I think it's in their heads. It may be implicit, it may be explicit, but if we can get it out there and provide it to everyone, I think we're all better off. I mean, we all tend to specialize, right? There's no one person that knows it all.
Mehmet Akşit, University of Twente.
So there it is.
We have done similar experiments with companies. I mean, the change analysis and the organization analysis and so forth. Conclusion was that we couldn't get that useful statistical information unless we could identify the problem and what we call problem and solution concerns. So we needed to have some sort of concern tracing, what we called. So some things, the ripple effects or changes, sometimes they look terrible, but it's perfectly logical and not that bad. So we needed to know what were the requirements. Is the bug fix? Is the new feature? Mm-hmm. And how do they solve this problem? And the mostly solution domain and problem domain is not one-to-one, so it scatters. So our conclusion was that always there must be a standard way in order to address this, at least semi-automatically, what the concerns are and what the solutions are. So we needed to have some concern tracing to get meaningful explanation. So we couldn't do only by statistical analysis.
Mm-hmm. Right, so that's a great point. A couple of things that I want to say is, first of all, if you looked at the curve of how long it took machine learning to overtake symbol system reasoning and sort of be the dominant form of AI today, it was probably a decade, so, and with lots of people working on it. So I think, there are lots and lots of kinds of statistical analysis that one could apply, lots of ways of modeling things, and I think it's a kind of a hard problem to figure out what the most effective way is, but I see that as kind of a long-term goal. Mm-hmm. I don't see it as kind of something that any one of us is very likely to solve, in a few months or a year or something. But the particular pointer that you gave towards what it is that needs to be identified in order to learn these things is really important. And I hope that's out there in the literature, because there may be other ways of kind of automatically detecting those things as well, separated into two separate problems, right? Mm-hmm. So you build concern graphs or however you're representing the concerns with one technique, then use that to inform other kinds of analysis. I don't know what the right approach is, but I'm just betting that as time goes on, we're going to get better and better at it.
Okay.